Yeah, Mars is cooked. And honestly, so are we. Number 10. No plate tectonics. Earth has a trick that keeps it alive. Old ocean floor sinks into the deep, melts, and volcanoes push fresh gas back into the air. This recycling loop has run for billions of years, and it keeps the atmosphere topped up. Mars never built one. The crust sat under what geologists call a stagnant lid, a single unbroken shell that refused to crack and dive. No subduction meant no way to pull carbon back into the mantle and cook it into fresh volcanic gas. Olympus Mons and the Tharsis Bulge prove Mars had volcanic muscle, but those eruptions were one-way streets. Lava poured out, gases escaped, and nothing went back down. As the interior cooled, the eruptions grew weaker and less frequent. The last major flows on Tharsis may have ended only a few 100 million years ago, but by then the damage had been done long before. Minerals in the soil tell the rest of the story. Clays and sulfate salts formed when water reacted with rock, and those reactions pulled hydrogen and oxygen out of circulation permanently. Every mineral that locked in a molecule was one that would never return to the atmosphere. On a world with shifting plates, those minerals would eventually get dragged down and recycled. On Mars, they just accumulated. The supply line dried up while the losses kept mounting. Number 9. Mars S. Small size. Simple physics, and that is what makes it so unsettling. Mars has roughly 1/10 the mass of Earth. Smaller bodies radiate heat faster because they have more surface area relative to their volume. David Stevenson at Caltech has spent decades modeling how planetary interiors evolve. His work shows that a body this size bleeds heat so fast that its core stratifies, its mantle stiffens, and the internal engine that drives magnetic fields and volcanism winds down inside a billion years. Less internal heat meant fewer eruptions to replenish the atmosphere. Less radioactive fuel meant the core could not sustain the churning convection needed to generate a global magnetic field. Once that field collapsed, the gas envelope was exposed to the full force of the solar wind. Meteorite studies back this up. Samples from Mars show signatures of an early active core followed by a long silence. The InSight lander S-seismometer confirmed the core is larger and less dense than expected, consistent with a body that differentiated quickly and then cooled. A bigger Mars might have held onto its field and its air. The world did not fail because of bad luck or a cosmic accident. It was born too small to sustain its own internal machinery past the opening act. Number 8. Atmospheric escape. Bruce Jakosky built his career chasing this question. As principal investigator for MAVEN, he designed a spacecraft specifically to watch Mars bleed. MAVEN arrived in orbit in 2014 and immediately confirmed what models had predicted. Ions stream away from the upper atmosphere at a measurable rate even now. During solar storms, that rate spikes dramatically. Extrapolate backward 4 billion years to a younger, angrier sun, and the math is grim. Solar wind slammed into the upper atmosphere and knocked atoms free through a process called sputtering. Ultraviolet light split water vapor into hydrogen and oxygen. Hydrogen, the lightest element, escaped easiest. The heavier oxygen either followed or reacted with iron in surface rocks, staining them the red we see today. Jakosky's team measured the ratio of heavy to light hydrogen in what remains, and concluded that Mars lost enough water to cover the entire surface in a global ocean roughly 20 to 80 meters deep. None of it vanished in a single catastrophe. It trickled away over billions of years, molecule by molecule, while nothing stood in the way. What is left is less than 1% of Earth's atmospheric pressure. Almost pure carbon dioxide, too thin to trap meaningful heat, too thin to keep liquid water stable on the surface. Number 7. Core cooling and dynamo shutdown. 4 billion years ago, Mars had a functioning magnetic field. The evidence is written into the oldest rocks on the surface. Southern Highland crust carries strong magnetic signatures that could only have formed while a global field was active. The field was generated the same way Earth's works today. Liquid iron churning in the core, driven by heat from below, creating a self-sustaining dynamo. But the dynamo needs a temperature gradient to keep the convection going, and Mars could not maintain one. David Stevenson and others have modeled what happened inside. Iron, sulfur, and light elements in the core began separating into layers, like oil settling on vinegar. Once stratified, the core stopped convecting. The dynamo sputtered and went quiet. Benjamin Weiss at MIT has studied magnetic signatures in Martian meteorites and pinned the shutdown to somewhere around 4.1 to 3.7 billion years ago. The timing lines up with a sharp transition in surface geology. Rivers and lakes that carved the oldest terrains disappear from the record shortly after. The connection is direct. Lose the dynamo, lose the magnetic barrier. Lose the barrier and the atmosphere starts bleeding. The interior failure cascaded outward until it reached the surface. Number 6. Obliquity chaos. Earth's axis tilts at 23.4 degrees and barely moves. The stability is no accident. The Moon's gravitational pull acts like a gyroscope, locking the tilt within a narrow 2-degree range over tens of thousands of years. Mars has no such anchor. Jacques Lascar at the Paris Observatory ran the definitive simulations in the 1990s and showed that without a massive moon, the obliquity swings chaotically between 0 and 60 degrees over millions of years. Phobos and Deimos are too small to matter. At low obliquity, the poles freeze solid and trap volatiles in thick ice caps. At high obliquity, the poles face the sun directly and the caps sublimate in massive pulses, flooding the thin atmosphere with vapor that quickly redistributes to lower latitudes. The geological evidence matches. Ice deposits sit in mid-latitude regions where they cannot be stable under today's tilt. Layered terrain near the poles records dozens of cycles of buildup and collapse, each one matching a predicted obliquity shift. Francois Forget's climate group in Paris has modeled what these swings do to surface conditions. A world that never reaches equilibrium. Water and carbon dioxide constantly migrate between poles, atmosphere, and subsurface, never staying in one place long enough for a stable climate to hold. Earth got a moon, Mars did not. Number 5. Carbonate sequestration. For decades, there was a glaring problem with the Mars story. If the atmosphere was once thick with carbon dioxide, where did it all go? Escape to space accounts for some of it, but models kept showing the numbers did not add up. A huge reservoir of carbon was missing. Edwin Kite at the University of Chicago has been working on this puzzle for years. The idea is straightforward. When carbon dioxide dissolves in water and the water contacts iron-rich or magnesium-rich rock, chemical reactions produce carbonate minerals. Those minerals lock the carbon into solid crystal lattices permanently. The problem was evidence. Orbital spectrometers scanned for carbonates for years and found only small patches, nowhere near enough to account for a thick, ancient atmosphere. Then Curiosity drilled into sulfate-rich layers on Mount Sharp inside Gale Crater and found siderite, an iron carbonate hidden beneath a mask of magnesium sulfate salts. The masking salt made the carbonate invisible to the near-infrared instruments orbiting above. The carbon had been there all along, camouflaged. If Gale Crater is representative, then a massive carbon reservoir sits locked in the crust. Kite-S models describe a self-reinforcing decline. Each carbonate reaction removes carbon dioxide from the air, which weakens the greenhouse, which cools the surface, which reduces liquid water available for more reactions. But by the time the reactions slow down, the atmosphere has already crossed the point of no return. Clay minerals added a second trap. Water percolating through olivine-rich crust converted dissolved carbon dioxide into methane that became locked in clay lattices. Between carbonates and clays, Mars buried its own insulation and could never dig it back out. Number 4. Solar evolution. The sun that shines today is not the sun that shone on young Mars. Standard stellar models show the early sun was about 30% dimmer in visible light 4 billion years ago. By all rights, Mars should have been a frozen wasteland from birth. Dimmer does not mean gentler. The young sun blasted far more extreme ultraviolet radiation and drove a solar wind several times stronger than today. Kevin Zonley at NASA Ames has modeled what that radiation did to unshielded atmospheres, and the results are severe. Extreme UV hit the upper atmosphere and split water molecules apart. It energized ions enough for the solar wind to sweep them away. It drove photochemistry that broke apart greenhouse gases. All of this happened fastest during the first billion years, exactly the window when Mars needed its atmosphere most. MAVEN measurements confirm the process, continues today with a much calmer sun. Scale that rate up to match early solar output and the cumulative loss over 4 billion years becomes enormous. Mars needed to build atmospheric pressure through volcanic outgassing while simultaneously losing gas to a star's tearing molecules apart faster than eruptions could replace them. Earth won that race because it was bigger, kept its dynamo running, and had a thicker atmospheric buffer. Mars lost. Stellar models show the extreme UV dropped sharply after roughly the first 700 million to 1 billion years. By then, the magnetic field had already failed and the atmosphere was too thin to recover. The window closed. Number 3. Hemispheric magnetic dichotomy. Something strange shows up when you map magnetic signatures across Mars. The southern highlands carry strong crustal magnetism, the kind that forms when rock cools in the presence of a global field. The northern lowlands are almost completely blank. Robert Lillis at Berkeley SUS Space Sciences Laboratory has mapped this boundary in detail using data from Mars Global Surveyor and MAVEN. The line between magnetic and non-magnetic crust is one of the sharpest geological boundaries in the solar system. Two competing explanations exist and neither has been ruled out. The first is a giant impact. A collision large enough to create the Borealis Basin, which covers most of the northern hemisphere, would have heated the crust above its Curie temperature and erased any magnetic memory. The basin is one of the largest confirmed impact structures known, and its outline roughly matches the demagnetized zone. The second is an asymmetric dynamo. Computer models show that if one hemisphere of the mantle was hotter than the other, perhaps due to uneven radioactive heating, the core could generate a field strong on one side and weak on the other. The north may never have been properly magnetized in the first place. Benjamin Weiss has examined both hypotheses using paleomagnetism in Martian meteorites. The evidence is frustratingly ambiguous. Both mechanisms could explain the data. What matters is the consequence. Whether the north lost its magnetism to a single blow or never had strong protection, that hemisphere was more exposed. Atmosphere above unshielded crust erodes faster. The dichotomy may have determined which parts of Mars died first. Number 2. Impact events. Early Mars took enormous hits. The Hellas Basin is 2,300 kilometers across and 7 kilometers deep. Argyre is nearly as large. The proposed Borealis impact, if confirmed, reshaped an entire hemisphere. Kevin Zanley and others have modeled what happens when objects that size arrive. The energy is staggering. A Hellas scale strike delivers enough heat to the mantle to disrupt convection patterns for millions of years. If the collision is large enough, it can temporarily restart a dying dynamo, or more likely, destabilize one that was already weakening. The atmospheric effects are equally brutal. A large enough strike can blast a measurable fraction of the gas envelope directly into space. The impact vaporizes rock and water, creating a temporary steam atmosphere that eventually escapes or condenses and freezes. Shockwaves propagate through the crust and trigger volcanic outgassing across wide regions, but the burst is temporary and the long-term losses outweigh the gains. Orbital magnetism maps show blank spots directly over the largest basins. The correlation is hard to dismiss. Those strikes likely heated the crust past the temperature where magnetic minerals lose their memory, adding to the evidence that each major collision weakened Mars' ability to protect itself. The timing matters. Most of the largest impacts happened during the late heavy bombardment, roughly 4.1 to 3.8 billion years ago. This overlaps almost exactly with the period when the dynamo was failing and the atmosphere was beginning its long decline. The bombardment did not cause the decline by itself, but it almost certainly accelerated a collapse that was already underway. Number 1. Microbial climate feedback. This is the theory that keeps astrobiologists up at night. It suggests Mars may have killed its own habitability and that life itself pulled the trigger. Robin Wordsworth at Harvard has modeled what happens when methanogenic microbes, organisms that consume hydrogen and carbon dioxide and release methane, colonize a young world with a thin, hydrogen-rich atmosphere. The initial effect is warming. Methane is a potent greenhouse gas, and biological production could have raised surface temperatures enough to sustain liquid water. Good news on the surface. But Wordsworth-S models show a lethal second act. As methane accumulates, ultraviolet sunlight breaks it into complex hydrocarbons that form a high-altitude haze. The organic haze reflects incoming sunlight before it reaches the surface, increasing the albedo. The net effect, after accounting for both greenhouse warming and haze reflection, can be cooling. If methanogens bloomed aggressively enough, the cooling could tip the climate past a threshold within tens to hundreds of thousands of years. Water freezes, ice covers the surface. The chemical feedstock for the methanogens disappears. The organisms that triggered the cooling die along with everything else. The idea is controversial, but it is grounded in published atmospheric chemistry and testable with future missions. If we find fossilized methanogens alongside evidence of a rapid cooling event in the same geological layer, it would be strong evidence that biology drove Mars over a climate cliff. On Earth, life remade the atmosphere too. Cyanobacteria flooded the air with oxygen and triggered the Great Oxidation Event, which nearly sterilized the surface before new organisms adapted. The precedent exists. Life is a geological force, and geological forces do not always act in their own interest. The chilling possibility is not just that Mars lost a war against physics. It may have been undermined from within by the very organisms that called it home.